So, welcome everybody, lecture number 12, analyzing sentences in the course Foundations of Language Technology at TU Darmstadt. If you want to prepare for this week, of course, go back to the last lecture and see what we did there. And also another form of preparation is to go to the NLTK book, chapter number 8, which is exactly on the same topic as our today's lecture. As usual, we give a small recapitulation of the last lecture. In the last lecture, we have seen how we go from raw text, as encountered in natural language, to a list of triples or tuples which contain entities and their relations. In this context, we have seen how to do chunking, because entities are usually embedded in chunks. So we have seen how to split up a sentence into smaller components, and these smaller components are individual chunks, such as noun phrase chunks or verb phrase chunks. We have seen how to use bio-tagging to get a chunking representation of a sentence, and we've also seen how this biorepresentation is equivalent to like a small tree-based tree-based notation of the sentence. We've then seen how to do named entity recognition, and similarly how to induce a chunking system to identify all textual mentions of named entities, or to do chunking automatically. And we've said that there may be two sub-goals of named entity recognition, namely identify the boundaries of the named entities, which are given by this bio-tagging scheme. And then secondly, identify the type of the named entity, such as a person, organization, or something similar. We've also seen what named entity recognition may be useful for in more high-level NLP tasks, such as information extraction or question answering. Today we're going further up the linguistic hierarchy to do syntactical, grammatical analysis of sentences. So in this lecture in particular, we're going to see how to use and define formal grammars. So of course you know the concept of grammar from school, but here we're also going to introduce something what we call a formal grammar, which is like a mathematical definition of a grammar to describe the structure of a sentence. And then secondly, how to develop computer science and NLP tools, which are called parsers, to automatically analyze sentences and build syntax trees. So first, we look at a certain property of natural language in terms of grammatical structure, namely the unlimited possibilities of constructing novel sentences. So consider a simple sentence such as Usain Bolt broke the 100-meter record. We can construct a novel sentence by saying, so let's call this sentence S by saying the Jamaica observer reported that S. Now let's call this sentence S prime here. We can construct a new sentence saying Paul said S prime. So Paul said the Jamaica observer reported that Usain Bolt broke the 100-meter record. And we can continue with this process apparently indefinitely by, let's say, using another construction such as I think S double prime, right? So I think Paul said the Jamaica observer reported that Usain Bolt broke the 100-meter record. So we now have identified some templates for building novel sentences from original sentences S. So a template would be Paul said S, I think S but S, as when S. Can you think about further templates? Of course you can. You can make S and S, S or S, as if S. So there are many other templates that you could use to construct bigger sentences from smaller. So from this we already see, from these examples we already see that sentences can be extended indefinitely, and that we could, at least in principle, understand sentences of arbitrary length that we've never seen before. Not only are the illustrations on the last slide exemplifications of this principle, arbitrary length and never seen before, but also we could think of simpler examples such as the wheel was spinning and spinning and spinning, which could apparently be continued indefinitely. And now when I say here arbitrary length, we also of course need to take into account natural limitations for humans, such as the day has only 24 hours and we need to go to sleep at some point. And we also have rather restrained cognitive limitations, such as that we cannot remember arbitrarily long information at one point. We just lose our attention span, so to speak, and our memorization capabilities. But at least in principle, that holds that it could be of arbitrary length, and it certainly can be novel. So now let us talk about the purpose of a grammar. We could say the purpose of a grammar is to give an explicit description of a language. And then we could have two questions about this. The first question could be, is grammar just a large but in principle finite set of observed utterances and written text in our mind that we can have access to? And given our previous two slides and previous comments, we would negate this answer and we would say, no, it's not a finite set, it's really infinite. We can construct novel and novel things from let's say from base sentences and some operations on those base sentences. Then the second question, is it maybe something more abstract, like the implicit knowledge that competent speakers have about grammar? And in a sense we would answer this yes, with the question yes, it's certainly not a finite set, but it's most likely something more abstract and more abstract rules, and this may be implicit, so it may be embedded in our minds, in our brains, but we do not have an explicit representations of that. And now in terms of a grammar in computer science terms, or like in more mathematical modeling terms, can make this implicit knowledge explicit by postulating some abstract processes to derive novel sentences. And this is, for example, what a generative grammar is doing. So a generative grammar is trying to satisfy this principle here, namely to give an explicit description of a language. And a generative grammar would do it as follows. So in a generative grammar, a language L is considered a set of all grammatical sentences. That means if L contains a specific sentence, we call the sentence as grammatical. And then a grammar, a generative grammar G, that is a formal thing, it's a formal notation that we can use for generating members of this set L here. So S generates a sentence S, so the grammar is like a mathematical notation, a formal mathematical notation that allows us to generate a sentence S, and then all the sentences S that G generates is called the language generated by the grammar G. And a typical notation is that we have recursive productions in a generative grammars of the form we've seen previously, such as a sentence can be induced by taking a sentence and another sentence, some more elementary sentences, that we then combine using the word and, or, although, if, however, etc., etc. So this is a typical formal notation that would occur in one element of a generative grammar G. Now, in natural language, as I have repeatedly argued in this lecture, we have a lot of ambiguity. Consider the sentence, while hunting in Africa, I shot an elephant in my pajamas. So today such a sentence would of course be totally politically incorrect, but let's abstract away from the meaning of the sentence and just look at its grammar. So that could be a picture that comes to your mind, and the question would be, how the hell did this elephant get into my pajamas? So in here, if you see this picture, you see the inherent ambiguity that we have at least two interpretations of this sentence that each goes with a different grammatical analysis. And this different grammatical analysis can be illustrated here. And here now you don't yet know about the formal structure of a grammar, but this allows these two graphs give you some intuitive description. So intuitively, the first sentence consists of a noun phrase and a verb phrase, and a noun phrase, and the noun phrase is a single pronoun I, and the verb phrase consists of all of this part here. And this verb phrase goes into a verb shot. I shot. And now what did I shoot? I shot a noun phrase, and this noun phrase is the element who is in my pajamas. So this is the picture representation and the picture interpretation of this sentence here. And the other one, the more classical interpretation, namely that I shot an elephant and I was in my pajamas, so this is the more classical interpretation that we would give the sentence, would have a different grammatical form with respect to this grammar formalism that we outline here. Namely, in this other grammatical form, we would have a noun phrase and then a verb phrase, and this verb phrase goes to another verb phrase, namely shot an elephant, I shot an elephant, and then to a preposition phrase, which also relates to me, namely I was in my pajamas. Good. So what we see from those two grammars here is that words combine with other words to form units. So that's what you see here. So those two words combine to form a unit. And then those three words here, so then we have a unit here and another word, we can and this would form another unit. Okay. Now what we observe from the last picture is that words combine with other words to form units. So let's go back to the picture. We see here my pajamas. Those two words form together to form a unit, and then we have this unit and another word. They form to combine a higher unit, and so on until the top. And those units are often called in linguistics constituents. And how do we know whether something is a constituent or not? Linguistic theory has developed a couple of tests to identify constituents. Let's take the sentence, the little bear on the tree saw the fine fat trout. So we can, in principle, substitute the little bear here by he. Well, that would not read perfectly in English, but at least in principle it could be done. He on the tree saw the fine fat trout. Similarly, we could replace the fine fat trout by it. The little bear on the tree saw it. So the fine fat trout would also appear as a constituent. In contrast, the little bear on the tree saw cannot be easily replaced by a single unit, all right? So therefore, we would not call it a constituent. There are other tests that linguists have developed, for example, moving to the front, coordination, fragment answers. What is moving to the front? Well, if you can move something to the front, it would be considered a constituent. You can do this in English, for example, the fine fat trout, you can move it to the front. The fine fat trout is what the little bear saw on the tree. So in English you need to have to rephrase the last part a little bit, but in principle you can move it to the front, so it's likely going to be a constituent. And as I've said, there are other tests, but those are not now of major importance to us, so I'm not going to go into them. Those constituents may take different forms depending on the syntactic theories. So like the grammar is and has been a big field in linguistics, so different syntactic theories have come up with have arisen, and those different theories, they define constituents all a little bit differently. For now, what we do in natural language processing is we take phrases as constituents, right? So this is the classical approach in NLP, that we call those constituents phrases. And a phrase is something that we've seen in the last lecture, where we introduced noun phrases. So a noun phrase, for example, consists of a head, which is the noun, and some subordinate parts such as adjective or article, which the noun governs. And as we've already seen in the last in the previous slide, a sentence can be broken into different constituents, and these constituents in natural language processing are then referred to as phrases, such as noun phrase, preposition phrase, verb phrase, and another verb phrase here. So we have syntactic heads, which means that each phrase, as we have, has a distinguished word, which is called its head. And the head determines which kind of phrase it is. As I've said, in a noun phrase, the head is a noun. The little bear, these fine leather jackets. So we would have, so that is part of some other sentence. We would have two noun phrases here. The first one is the little bear, where the syntactic head is bear, which governs. So that's also terminology which governs its subordinate words, such as the little. These fine leather jackets. Leather jackets is also a syntactic head, which then governs these fine. And within leather jackets, we have another syntactic head, namely jackets. For a verb phrase, the head is a verb: to eat cheese, to jump up and down, gave you the book. So those are the heads of verb phrases, and they govern something else. In this case, pronoun and a noun phrase. The head of an adjective phrase is an adjective, as you would imagine, such as full of toys, very happy. And the head of an adverbial phrase is, as you would imagine, an adverb, very carefully, slowly. Is an illustration of this. Now let's talk about a popular grammar formalism in natural language processing, namely context-free grammars. Context-free grammars look as illustrated here. They have derivation rules. A symbol expands into other symbols. This is what we've previously seen in those tree structures. Basically, if you apply a grammar to a novel sentence, you'll get exactly such a tree structure as we've seen here. And that's what we're gonna do now. Now, as I've said, a grammar, a context-free grammar is a set of those expansion rules. So you would have like that the sentence expands into a noun phrase and a verb phrase, whereas a verb phrase expands into a verb and a noun phrase, or alternatively, so the pipe here stands for or, like this is either this, or it expands into a verb, NP and PP, and then further down the letter, you see also the lexical expansions. So, for example, a verb can be saw, at, walked. A noun can be man, dog, cat, telescope, park, etc. And a preposition could be in, on, by, and with. So this is a simple grammar that you can come up with. So you could say, well, that's basically how my simple English behaves. And then in NLTK, you can directly write this down as a string and feed this string into a method of NLTK CFG. So CFG stands for context-free grammar, and then you would say from string and feed in your grammar. Then if you want to parse a simple sentence such as Mary saw Bob, you would first feed in your grammar to the NLTK recursive descent parser, which we're going to see in a short while how that works. You get a parser object, and then you say, please parse my sentence, and what it will give you as output is it will give you different subtrees in the parse tree. So it will give you the whole parse tree as we've previously seen, and then you can print out the subtrees in this tree, and you'll get exactly what you see down here, namely that the sentence consists of the subtrees a noun phrase, which is Mary, and a verb phrase, which is goes into saw and Bob. Now we typically have recursion in syntactic structure. This is what we've seen in the motivation slides given earlier, that we can really generate an infinite amount of novel sentences, and that's where we need what we need this recursion for. Like formally we say, if a category or like if a symbol occurs on the left and also on the right of a rule, the grammar is said to be recursive, and that's going to be a recursive rule. So if you have like a nom, whatever a nom is, goes into an adjective and another nom, that is a direct recursion. The recursion could also be indirect, when you say a sentence goes into an NP and VP, and the VP in turn expands into V and S. So you could directly say a sentence, so that is an indirect recursion because it's not directly on the left and right side. But if you rewrite this, so you could rewrite this into a sentence goes into noun phrase, verb and S, then it would become a direct recursion. Okay? And if you have such a recursion, then we can really construct an infinite amount of sentences as illustrated previously. So the sentence here in this example is a sentence expands into a noun phrase and a verb phrase, whereas the noun phrase then becomes the word chatterer, which is a proper name, as you've seen here in the part of speech, and the verb phrase is what. So chatterer is doing what? He said something. He said. And he said what? He said another sentence. And the other sentence is, just as in our initial illustrations, similar as in our initial illustrations, it is a sentence like Buster thought the tree was tall. So Chatterer said, Buster said the tree was tall. So we have a sentence here, so that is the recursion, right? So a sentence goes into a sentence, which goes into another sentence, which allows for unlimited construction of novel sentences in our grammar. Now let us go next to how we do parsing with context-free grammars. Let's come to the real practical application. So what a parser is doing, a parser is processing input sentences according to the productions of a grammar. It builds one or more constituent structures conforming to the grammar. To find conforming structure, it searches through the space of all possible parse trees according to the grammar. And parsers can be built up using various approaches, for example a top-down parser, which such as recursive descent parsing, where it goes top-down from the top production, which is sentence goes to noun phrase, verb phrase, etc. So it goes from the top of the tree down. And a bottom-up parser, which starts out at the leaves, so it starts out with the verbs, maps them into their part of speech, for example, and then recursively builds higher structure until it reaches the. So we start out with recursive descent parsing. Recursive descent parsing interprets a grammar as a specification of how to break high-level goals into lower-level sub-goals. So one starts out with so the highest level goal is to construct a valid sentence. Then we check the sentence productions that we have. For example, a sentence expands into a noun phrase and a verb phrase, and then we have two new sub-goals, namely to construct a valid noun phrase, and the second goal, once that is satisfied, is to construct a valid verb phrase. The lowest level goals, such as construct the verb telescope, can be directly compared to the input sentence. So we check whether we have any match, and if so, if we have a match, then a possible part of a parse tree was found. For example, we can complete our noun phrase. Otherwise, if there's no match, if we cannot explain the data at the bottom, we need to do backtracking and try out. So that's what's called backtracking. So we try out other options. Let us do an example parse. So in recursive descent parsing, we start with the initial so we start with S. We want to we have our high-level goal to construct a parse tree for the sentence. So now let's say in our grammar we're going to choose S expands to NP VP. Maybe this is our only rule that involves S on the left-hand side, or maybe this is the first rule that involves S on the left-hand side. So then we're gonna choose this rule. We're gonna say NP S expands to NP VP. Now we have our subordinate goal to do something meaningful with NP. So let us choose NP goes to determiner noun. So then we select for determiner, we select the, and we check whether we have such a rule in our grammar, and indeed we do have, so we have matched it, so we're doing fine. Then we are selecting noun expands to man, and we check. However, we see that this is not a match of the actual data, because here we have dog, so we need to backtrack and select n expands to dog. And then we once we have this, we have completed our NP. Now we can do our VP, and we do it in the same way. We're going down to the bottom. So for VP we have 3 sub goals, namely V, NP, and PP, and we try to match each of them. And note that this backtracking. So once we're at a certain stage, so let's say we can complete this here, but we can also backtrack then here, and even though we could complete something, we backtrack to find more valid parses. So each sentence may not only have one parse tree, but it may have several parse trees. So we can backtrack at each position to find alternatives, right? And note in this particular case here with the dog saw a man in the park, we would also have like depending on our grammar. So that of course depends totally on our grammar, but intuitively we have at least 2 interpretations, similar to saw a man with the telescope. So the seeing could be combined with in the park, see with the telescope, see in the park, or the in the park could be attached to the man, a man in the park, a man with the telescope. But as I said, it really depends on the grammar that we have specified, like this. So in this case, in our previous illustration, this was our grammar. If we have a different grammar, we may have different possible syntactic analyses of any given input sentence. So as we've previously seen, NLTK provides already a recursive descent parser implementation, so you can just try it out yourself, as we've done previously. Feed in your grammar, feed in your input sentence, and then parse it. So what are shortcomings of the recursive descent parser? So one problems are left recursive productions. What does left recursive mean? Well, it means if so first, a recursive production is where the same symbol appears both on the left and the right of the arrow. Now left recursive is if the symbol to be expanded is the leftmost symbol on the right hand side. So this is the right hand side, this is the left hand side, and this is the leftmost symbol, and this is the rightmost symbol. So if the repeated element is the leftmost symbol, we have a left recursive production, and that will cause an infinite loop. So basically it tries to achieve this subgoal NP, then to achieve this, it again needs to achieve the subgoal NP-PP, and it will just expand it by this same production again. So our parser will never terminate. Well, to circumvent this problem, you would have to rewrite your grammar and remove left recursive productions. Secondly, a lot of time is wasted considering words and structure that do not correspond to the input sentence, because you try out everything, right? You try N goes to man, so the noun goes to man, the noun goes to cat. So you try out all of them just to check whether it matches the actual data, which is a waste of time. And so when we do our backtracking, we may need to discard a whole phrase which gets lost by the backtracking, and then afterwards we may again need to identify a similar phrase. So we have to repeat our work using backtracking. Some of these problems are inherent to top-down parsing, because top-down predicts what the input will be. It doesn't look at the before inspecting it. So it doesn't look at the input. It just goes from the top and tries to predict what's coming out, rather than looking at the input directly. So this is what the advantage of bottom-up parsers, or like the shift-reduce parsing. They directly look at the data and then try to produce the grammatical analysis. And note that this differentiation of top-down versus bottom-up is also used more generally in science to describe either formalisms or theories that start from the data. So they look at the inputs, that's the actual data, and then build a theory or a formalism on top of that, or a formalism or theory which starts out with the theory and then tries to explain its data. So there's a demo which you can try out on your local computers by typing in this functionality. Let's talk about our second parsing strategy, which is called shift-reduce parsing. Shift-reduce parsing is a simple bottom-up parsing approach. What it's doing is it's trying to find words or phrases, such as noun phrases, verb phrases, that correspond to the right-hand side of a grammar production, and then it's going to replace this right-hand side by the left-hand side of the production rule until everything is reduced to the sentence symbol S. So, and this indicates that we have successfully parsed the sentence. The procedure is as follows. We have two operations. The one operation is called shift and the other is called reduce, and those two operations give the name for the parsing technique. So we have two operations, and we also have two arrays or two data structures. The one data structure, that's a list, for example, that stores our input words, and another list which we call stack, on which we process the symbols until we hopefully reach the terminal symbol S, like the sentence symbol S. So what we do is we check our stack and we check the top n items. Let's say n could be 2, 3, whatever, however, whatever is appropriate for our production rules. So we check the top 10 items and check whether they match the right-hand side of any production rule in our grammar. And if they do so, we remove the top n items from the stack and combine them to a partial parse tree with a left-hand side production and push the partial parse tree back on the stack. Okay, and we are finished when all input is consumed and only a parse tree with root node S is left on the stack. So now this is like the abstract description. Let's do it by an example and you'll easily see how it works. So let's say we have the sentence, the dog saw a man in the park. What we're gonna do is we're gonna push, at the beginning we really have nothing to do except for pushing elements on the stack. So we're gonna push the first word in the input onto the stack, and then we after we've pushed that, we see that we cannot do any operation with that, so we cannot do a reduce operation. So what we're gonna do is we're gonna push also dog on the stack. And here I have to say that actually when we push the on the stack, we can do one reduce operation. We can say the is a determiner, so we're gonna replace this by determiner. And then next we're gonna push dog on the stack, and we're gonna replace dog by noun right away. So then we have determiner noun on the stack, and we have the remaining text in the input data structure. So now what we're gonna see is the dog can matches the right hand side of a production rule, namely noun phrase expands to determiner noun. So we're gonna reduce this to noun phrase. So noun phrase will be left on the stack. And then we're gonna continue to push. So we're gonna push saw on the stack, and we say that and we're then gonna reduce it to a verb. Then we will push a man on the stack, reduce it to determiner noun, and subsequently to noun phrase. So we're always gonna check the top items on our stack. Okay? So we'll continue with this for a long while until we have noun phrase, verb, noun phrase on the stack. And we're going to combine verb and noun phrase to another noun phrase. Then we're going to combine this verb phrase and the noun phrase to a verb phrase. And then finally we have NP VP left. And we're going to combine everything to a stack, and we have successfully passed the tree. And note, all the while we have been doing this, we have kept track of the relationships. So initially we saw the dog has the corresponding production rules. Determiner expands to the, noun expands to dog. We've then also kept track of that noun phrase expands to determiner noun. So we store the complete tree while we are doing our reduce operations. Okay, so we not only have we consumed all the input and have left this, the symbol S on top of the step, but we've also stored our whole tree while we were doing those operations. So now, now we have available the complete pass tree. So in NLTK there is a simple implementation of shift-reduce parsing, which does not use any backtracking. So because there is no backtracking, it may end in a dead end. So assume it's doing something, it's reducing something, and it's leaving something on the stack which cannot be reduced further. So then no pass tree will be found by the algorithm that NLTK provides, even though there may actually be a pass tree available had backtracking been made use of. Secondly, shift-reduce parsers build each structure only once. So you only build it once, you don't do repeated work, in contrast to recursive descent parsers. However, as we've already seen, that they can reach dead ends if not implemented intelligently. So to make this more intelligent, we can include some conflict resolving strategies which are beyond our brief introduction of shift-reduce parsing, but they can be implemented, and this may circumvent the problem of dead ends. There's also something called generalized shift-reduce parsers, which are commonly used for parsing programming languages. So with such parsers, of course, you cannot only parse natural language, such as English, German, or French, but you can also parse programming language, such as Python or Java. And for this, you can also design grammars and then parse novel code with a parser, with a shift reduce parser. And as we've indicated here, they're gonna in such setups, a generalized shift reduce parser is being applied, because of course we don't want to have the problem of those dead ends and our compiler telling us that our code is not parsable, even though in principle it would be. As for the recursive descent parser, there's also a demo which you can invoke by typing this command here, and I'll leave this up to you, to your private investigation to do so.